Welcome. Today we're going to dive deep into a fundamental concept in precalculus, understanding sine and cosine using the coordinates of points on a circle. By the end of this lesson, you will be able to determine the exact coordinates of points on a circle centered at the origin, and you'll be able to find exact sine and cosine values for certain special angles. We'll be focusing on a topic from AP Precalculus, which builds a strong foundation for future math courses. Our main goal is to connect the familiar trigonometric ratios sine and cosine with the geometry of a circle. Let's start with a circle centered at the origin. Imagine a circle on the coordinate plane, with its center right at the point 0, 0. This circle has a radius which we'll call r. This radius is the distance from the center to any point on the circle's edge. Now, let's consider an angle, which we'll call theta. In trigonometry, we often place this angle in standard position. Standard position means the vertex of the angle is at the origin, and one of its rays, called the initial ray, lies along the positive x-axis. The other ray, the terminal ray, rotates counterclockwise from the positive x-axis by the amount of the angle theta. This terminal ray will always intersect our circle at exactly one point. Let's call that point P. This point P has coordinates, an x-coordinate and a y-coordinate. Here's the key connection. The coordinates of point P are directly related to the sine and cosine of the angle theta. The x-coordinate of P is r times the cosine of theta, and the y-coordinate is r times the sine of theta. This means any point P on a circle of radius r can be expressed as r cos theta, r sine theta. This formula connects the coordinates of a point to its angle and is the foundation of circular trigonometry. Now, let's look at the special case where the radius is 1. So, what happens if our circle has a radius of 1? This special circle is so important in trigonometry, it has its own name. It's called the unit circle. The unit circle is simply a circle centered at the origin with a radius of 1 unit. Let's apply our formula for coordinates to this unit circle. Remember, the general formula is P equals r cos theta, r sine theta. For the unit circle, our radius r is simply 1, so we can substitute 1 for r. This gives us P equals 1 times cos theta, 1 times sine theta, which simplifies to just cos theta sine theta. This is one of the most powerful ideas in precalculus. On the unit circle, the x-coordinate of the point P corresponding to an angle theta is the cosine of theta, and the y-coordinate is the sine of theta. Let's repeat that for emphasis. For any angle theta, the coordinates, x, y, of the point on the unit circle are precisely cos theta, sine theta. This means that if you know the coordinates of a point on the unit circle, you automatically know the values of sine and cosine for that angle. And if you know the angle, you can find the point, and thus it's sine and cosine. Now that we know the coordinates on the unit circle are just cos theta, sine theta, we can easily find the sine and cosine of angles that lie along the axes. Let's use the unit circle to figure out these values. Draw a unit circle. First, consider an angle of 0 radians. An angle of 0 radians means we don't rotate the terminal ray from its initial position along the positive x-axis. The point on the circle is 1, 0. Since the coordinates are cos 0, sine 0, we can see that cos 0 is the x-coordinate, 1, and sine 0 is the y-coordinate, 0. So cos 0 equals 1, and sine 0 equals 0. Next, let's look at an angle of pi over 2 radians. Pi over 2 radians is 90 degrees. This rotation places our point on the positive y-axis, at the coordinates 0, 1. The coordinates are cos pi 2, sine pi 2. This means cos pi 2 equals 0, and sine pi 2 equals 1. So we have our values for this angle. How about an angle of pi radians? Pi radians is a half circle, or 180 degrees. The terminal ray points along the negative x-axis, and the point on the circle is -1, 0. Here, the coordinates are cos pi, sine pi. We get cos pi equals -1 and sine pi equals 0. Finally, let's find the values for 3 pi over 2 radians. 3 pi over 2 radians is 270 degrees. The terminal ray points along the negative y-axis, and the coordinates are 0, -1. The coordinates are cos 3 pi / 2, sine 3 pi / 2. So cos 3 pi / 2 equals 0, and sine 3 pi / 2 equals -1. We have found the values for this angle. By using the simple coordinates of points on the unit circle, we found the exact values of sine and cosine for these important angles. In the next scenes, we'll see how to find values for angles not on the axes. So, how can we find the exact values for other angles, like pi/4? The key is to use geometry, specifically the properties of a special kind of triangle. We'll use an isosceles right triangle, also known as a 4-5-4-5-9-0 triangle. This triangle has two 45-degree angles, a 90-degree angle, and its two legs have equal length. By the Pythagorean theorem, a squared plus a squared equals c squared, which means 2a squared equals c squared. Solving for c, we find that the hypotenuse is a times the square root of 2. So, the side ratios are a and a times the square root of 2. It's often easier to think of the ratio as 1, 1, and the square root of 2. Let's use this triangle on the unit circle to find the values for the angle pi/4. Pi/4 radians is the same as 45 degrees. Let's draw this angle on our unit circle. The point on the circle is pxy. If we drop a perpendicular line from P to the x-axis, we form a right triangle. Notice the angle at the origin is pi/4, and the angle with the x-axis must also be pi/4, because 90 degrees minus 45 degrees is 45 degrees. This is an isosceles right triangle. The hypotenuse of this triangle is the radius of the unit circle, which is 1. Since the triangle is isosceles, the two legs, x and y, must be equal. So we know the hypotenuse is 1 and x equals y. Let's use the Pythagorean theorem on our triangle. X squared plus y squared equals 1 squared. Since x equals y, we can substitute x for y, giving us 2x squared equals 1. Solving for x, we get x equals 1 over the square root of 2. Rationalizing the denominator gives us the square root of 2 over 2. And since x equals y, y is also the square root of 2 over 2. So, for the angle pi/4, the coordinates are square root of 2 over 2, square root of 2 over 2. This means that cos pi4 equals the square root of 2 over 2, and sine pi4 equals the square root of 2 over 2. We've found another exact value. Now let's find the values for pi/3 and pi/6, using another special triangle. This time, we'll work with an equilateral triangle. An equilateral triangle has all sides equal and all angles equal to 60 degrees. We'll use this triangle to derive the 30-60-90 triangle. Let's assume our equilateral triangle has a side length of 2. So, all sides are 2 and all angles are pi/3, or 60 degrees. Now, let's bisect one of the angles. Drawing an altitude from the vertex to the opposite side creates two congruent 30-60-90 right triangles. Each of these new triangles has a 30-degree, a 60-degree, and a 90-degree angle. Let's analyze one of them. The original angle was 60, but the altitude bisected it into 30 degrees, or pi/6. The hypotenuse is the original side length of the equilateral triangle, which is 2. The side opposite the 30-degree angle is half of the base, so it's 1. Using the Pythagorean theorem, the third side is the square root of 3. So, we have a 30-60-90 triangle with side ratios 1, square root of 3, and 2. We'll use this to find our coordinates. Let's apply our 30-60-90 triangle to find the coordinates for the angles pi/3 and pi/6. First, the angle pi/3, which is 60 degrees. We'll draw this angle on our unit circle. Dropping a perpendicular to the x-axis creates a right triangle. This is our 30-60-90 triangle, but it's been rescaled to fit the unit circle. The angle at the origin is pi/3. This means the other non-right angle must be pi/6. The hypotenuse is the radius of the unit circle, which is 1. We know the ratio of sides in a 30-60-90 triangle is 1 to square root of 3 to 2. The side opposite the 30-degree angle, which is our y-coordinate, must be half of the hypotenuse. So, y equals 1/2. Since the hypotenuse is 1, y is 1/2. The side opposite the 60-degree angle, which is our x-coordinate, must be square root of 3 over 2 times the hypotenuse. So x equals the square root of 3 over 2. Since the hypotenuse is 1, x is the square root of 3 over 2. So, The coordinates for pi over 3 are square root of 3 over 2, 1/2. This gives us cos 3 equals square root of 3 over 2, and sine pi 3 equals 1/2. What about pi over 6, or 30 degrees? Let's draw this angle on the unit circle. Dropping a perpendicular creates another 30, 60, 90 triangle. This time the angle at the origin is 30 degrees. The side opposite the 30-degree angle is our y-coordinate, so y is 1/2. The side opposite the 60-degree angle is our x-coordinate, which must be square root of 3 over 2. So, for the angle pi over 6, the coordinates are square root of 3 over 2, 1/2. Notice that the x and y coordinates from pi over 3 have simply swapped. We now have the coordinates for all the main special angles in the first quadrant. In the final scene, we'll see how to use these to find values for angles in other quadrants. So far, we've only worked in the first quadrant where both x and y coordinates are positive. But what about the other three quadrants? How do we find the sine and cosine values there? The key is understanding the signs of x and y in each quadrant and using a reference angle. Let's first review the signs. In quadrant I, x is positive and y is positive. So cos is positive and sine is positive. In quadrant 2, x is negative and y is positive. So cos is negative and sine is positive. In quadrant 3, both x and y are negative, so cos and sine are both negative. And in quadrant IV, x is positive and y is negative, so cos is positive and sine is negative. Now for the reference angle. The reference angle for any angle theta is the acute angle formed by the terminal side of theta and the x-axis. It's always a positive angle between 0 and pi over 2. The magic of the reference angle is that it helps us find the coordinates. The x and y values for an angle are the same as its reference angle, just with different signs. Let's work through an example. The angle 2 pi over 3. This angle is in the second quadrant. To find the reference angle, we find the difference between 2 pi over 3 and the x-axis, which is pi. So the reference angle, which we'll call alpha, is pi minus 2 pi over 3, which equals pi over 3. So the reference angle is pi over 3. This means our coordinates will involve the values we found for pi over 3. Remember from our last scene, the coordinates for pi over 3 are square root of 3 over 2, 1/2. Now for the signs. The angle 2 pi over 3 is in quadrant 2. In quadrant 2, x is negative and y is positive. Since x is negative, our cosine value will be negative. Since y is positive, our sine value will be positive. So, we take the x and y values from the reference angle and apply the quadrant 2 signs. The coordinates for 2 pi over 3 are negative square root of 3 over 2, 1/2. Therefore, cos 2 pi slash 3 equals dash square root of 3 over 2, and sine 2 pi slash 3 equals 1/2. And there you have it. The unit circle is a powerful tool. By understanding its fundamental properties, the coordinates for special triangles, and the concept of reference angles, you can find the sine and cosine of any angle. In this video, we've accomplished our learning objectives by determining coordinates on the circle and using them to find exact trigonometric values. Keep practicing this technique, and you'll become a master of the unit circle.